In this video, we're going to talk about standard reduction potentials. So when we have our electrochemical cell, we have our anode and our cathode, and we have the half reactions that happen at each of those. So we have a half reaction for our anode, in this case our hydrogen anode, and then we have a half reaction for our cathode. We can add those together to get our overall cell reaction. So we know that when we add the anode half reaction and the cathode half reaction together, the electrons should cancel out so that we're left with no electrons in our overall cell reaction. Well, we can measure the standard potential of that cell, in other words, the voltage that we get out of that cell. The standard potential of a cell is the sum of the half cell potentials. So we have to take into account the cell potential for the anode and the cell potential for the cathode. If we add those together, we get the cell potential for the overall cell. So for example, if we're looking at this cell where we have hydrogen and copper, hydrogen acting as our anode and copper acting as our cathode, the overall cell potential that can be measured for that cell is 0.34 volts. So when we measure the cell potential, we are measuring it with two electrodes. We can't measure a cell potential with just one electrode because no electrons would be flowing. There would be no electrical current, so there would be nothing to measure. So we need two things in there. We need our anode and our cathode in order to measure voltage. Well, the problem with that is if we have both of them in there, we can't know what the cell potential is for each one. So the way that we solve that is we choose something to be the reference electrode. What we use typically as the reference electrode is what's known as the standard hydrogen electrode. So the standard hydrogen electrode is our H2, which can be oxidized or reduced depending on what else it's being measured with. So we have defined the standard hydrogen electrode to have a cell potential of 0 volts. Everything else is measured in relation to the standard hydrogen electrode. So whatever voltage we get when we measure something else in relation to a standard hydrogen electrode, that is the cell potential of that material. So for example, if we look at this cell that we were just talking about, in this case hydrogen acts as our anode and gets oxidized, and we have copper as our cathode. Well, we have defined the standard hydrogen electrode to have a cell potential of 0 volts. So if we measure a potential of 0.34 volts for the cell, that means that copper can be defined as having a cell potential of 0.34 volts. So this is an example of the type of setup we would have. So this would be our standard hydrogen electrode here. So we would have a tube here that has hydrogen gas in it, and we have some nitric acid here that produces H+ ions. And then we have, in this case, our zinc anode. And we have copper this time, hydrogen this time acting as the cathode. So electrons flow out of the zinc anode through the wiring into the voltameter and to our standard hydrogen electrode. And then we have our salt bridge here that's made up of sodium nitrate that connects these two to allow electrons to flow from one part of our cell to another. So in this case, we're measuring zinc against the hydrogen. So zinc is the one that gets oxidized, and hydrogen is going to get reduced. So we again have defined hydrogen to be 0 volts, because whether it's getting oxidized or reduced, we define the stearin hydrogen electrode as having a potential of 0 volts. So this cell produces a potential of 0.76 volts. That means that the potential for zinc is 0.76 volts. Now, typically when we put these in tables, we list them as standard reduction potentials. So if the cell potential when zinc is being oxidized is positive 0.76 volts, then the standard reduction potential will be negative 0.76 volts. So this is a table of standard reduction potentials. As I said, typically we list everything in terms of reduction potentials. If we want to know the voltage for oxidation, then we would simply reverse the sign. So something that's negative would become positive, something that is positive would become negative. So these are listed so that those at the top are our stronger oxidizing agents, and those at the bottom are our stronger reducing agents. So if you're looking at two of these and comparing, for example, if we were looking at zinc and copper, which is a common one to use as an example in electrochemistry, if we're comparing those two, zinc has the stronger reducing agent, copper is the stronger oxidizing agent. Now keep in mind, if you think back to redox reactions, this is the stronger reducing agent. That means that it is the one that is getting oxidized. So the stronger reducing agent is the one that gets oxidized. The stronger oxidizing agent is the one that gets reduced. So remember, an oxidizing agent is causing something else to be oxidized. If it's causing something else to be oxidized, that means it is getting reduced. The reducing agent is causing something else to be reduced, therefore it is the one that gets oxidized. So if we had a cell made up of copper and zinc, zinc is the stronger reducing agent, so it's going to cause copper to be reduced. Therefore, it's going to get oxidized. That means zinc is going to be the one being oxidized, so zinc is going to be our anode, where oxidation occurs, and copper is going to be our cathode, where reduction occurs. So if we were going to write a cell between zinc and copper, for zinc we would actually switch this, so it would be zinc forms Zn2 positive plus 2E negative, so it would have a voltage, it would contribute a voltage of positive 76 volts. And then copper would stay as it is. So if we look at that exact cell, so zinc is acting as our anode, copper is acting as our cathode. So the negative of a negative is a positive. So zinc is positive 76 volts. Copper, since it is the cathode, would stay what it's listed as in the table. So we would have positive 0.34 volts. If we add those together, this cell has a potential of 1.10 volts. If we take something like silver and copper, so if we go back to our list here, we already have copper here, and we have silver. Let's find silver here in the table. So silver is up here in our table. So that means that copper is the stronger reducing agent. So in this case, copper is going to act as the anode, and silver is going to act as the cathode. So the further down they are on the table, they have a stronger reducing agent, which means that they're going to get oxidized. So they're going to be the ones that are the anode. So copper acts as our anode. Silver acts as our cathode. Now we have to multiply the reaction for silver times 2, since silver only gains 1 electron. In order to add these reactions together, we need to multiply this by 2 so that the electrons will cancel out. So we would have 2 silver plus 2 electrons yields 2 silver. So the electrons would cancel out when we add these together to get our overall cell reaction. Now, when we multiply a reaction by 2, we do not multiply the cell potential by anything. So half cell potentials are intensive properties. They are not influenced by the quantity of matter that we have. So therefore we do not multiply them by a number just because we multiply the reaction by a number. So even though we multiply this reaction for silver times 2, we would not multiply the cell potential times 2. So if we look back at our table, silver has a cell potential of positive 0.80, copper has a cell potential of positive 0.34, but since copper is our anode, we reverse the sign. So we do reverse signs, we just don't multiply the cell potentials by anything. So 0.80 plus a negative 0.34 gives us a cell potential of 0.46 for the cell. So we will stop here and we'll talk more about electrochemistry in the next video.